let me share the screen. And to begin with, that's not where I want to be. Whoops. That's where I want to be. Today is October 15th. There is a quiz that is going to be open after class today, available after class time today, and it will be available till 11:59 p.m. tomorrow. What's going to happen is that you will, I will not be looking at papers if there is not one submitted. So you need to submit your work in Blackboard in order for me to look at the quiz and get the quiz grade into the Blackboard grade book. Homework 9 is due today and homework 10 is due today. I believe homework 9 is the definition of probability. Homework 10 is the probability with permutations and combinations. Today we'll be looking at the content of homework 11 and 12, which involve, we had looked at the probability of something not occurring. We're going to add the idea of or and odds, and then we're going to look at independent events, the word and conditional probability. Before we get started looking at all of that new stuff, does anybody have any questions on any questions or any questions about any of this?
On homework 9,
Yeah.
the first question and the last question I kind of struggled with.
All right, homework 9. First question and last question. First questions are from the textbook are the chapter openers. They're the like, let's think about all of this stuff. Then let's do the chapter and then let's go, the section openers, and then let's go back. First question says the hours of sleep that citizens get on a typical night is shown by the table to the right. A researcher in sleep deprivation finds that the average human needs at least 6 hours a night to function properly. What's the probability of getting at least 6 hours of night? Well, this is one of those empirical probabilities. We don't necessarily know a full sample space and all of the people and everything, but we've got this experiment. And we know that it's been done 300 times because we know there was a total of 300 people. We want to know of getting at least 6 hours of sleep. At least 6 hours of sleep would be 6 or more hours. And so that would be all of these people. And so the number of people who got 6 or more hours would be the 70 plus the 88 plus the 75 plus the 10 plus the 6. So I should be able to add that in my head. 70 and 88 is 158 and 5 is 160. Well, you get the picture, right? Is it okay if I just set it up? Then when you're going to do that, you're going to get a fraction. They're going to ask you to divide that to the decimal. And then you're going to move the decimal 2 places to change it into a percent. Any better, sir?
Yeah, that's good. Thank you.
Okay.
I could not get this problem too. I even email you in your answer and I try to do it and
Nothing?
nothing.
It's just the process makes sense, hon?
Yeah, it does.
Okay, so you're feeling a little bit better about it.
Yeah.
Okay. And then let's clear that and look at the last one. Okay, the target. When I look at the target, the total sample space is the total area. And so the total area is that big square, which is 21 times 21, which is 21 and 441. And now we want the probability that it'll land in the green. Well, in the green, we have 2 parts. we have the little square, which is 6 by 6 or 36. And then we have that, I almost want to call it, to me, it looks like a mat on a picture. Yes? And so if I look at that, the outer part of that, can you guys see where my pen is drawing around, is square 15 by 15. But I'm not taking, for that part there, I'm not taking the whole square 15 by 15. But do you see how we're kind of cutting the middle out of the square? And since we're cutting the middle out of the square, we're cutting this part out. We can think of subtracting that part, which is the 9 by 9. So 15 times 15 is, I think that's 225. Can somebody check my arithmetic? Because
Yeah.
225.
225 minus the, that should be minus, not minus the 9 times 9 is 81. And so that would give me 144. And so the total green is the 36 plus the 144, which would be 180. And so then the probability that I land in the green is the 180, the total of the green area, over the 441. And I'm looking at those numbers, and I think they're both divisible by 9. So dividing out 9, I get 20 over 4, heaven help me, 36, 49. And so the probability would be 20 out of 49. Should we see if we got it, or does that make sense, or any better?
Yeah, that makes sense.
Okay.
Thank you.
Great job. We did it. Anybody want to look at any others?
Yeah, I had a really hard time with the other homework assignment, the one that had like 10 questions. I think it was
The homework 10? Yeah.
Yeah, I like that one was really, really hard for me.
I'll tell you what, I think I told you at the beginning, I don't like to, as a rule, I don't like to describe things as really, really hard, because I don't want anybody to have their predetermined thought set. But I think that instead I described that homework 10 as the problems that most people find most challenging in this chapter.
Yeah.
So don't feel alone. They're the most thought-provoking problems. The lottery question is kind of over the top. And so I made a promise to the other section that I guess I'll promise to you guys. I promised that I'd turn that question into extra credit. And so can somebody please remind me when we meet again on Tuesday that I promised to give everybody the extra credit for that question, so that if you get it right, you know your score will be above 100. And if you don't get it right, you won't be penalized for it. Now, we don't have time today to look at all 10 of these. Is there any ones in particular that anybody wants to look at?
Could we go over 9?
Sure. You don't mean 9 of the 10, you mean question.
No, question 9.
Okay, all right. Question 9, what we've got, and I have to apologize, I think somebody sent me this one and I made a careless mistake, and I re-emailed them pointing out my careless mistake, so I hope that that's all right. But we've got 3 digits. We've got the digits 3, 4, 5, 6, 7, and they're being randomly arranged to form a 3-digit number. The digits cannot be repeated. Find the probability that the number is even and also greater than 700. So this was one of the ones, like the first one we did on that worksheet that I gave you guys with the softball team. And it's almost easier to, I think of filling in the blanks. But I digress. When we put together a number, doesn't the order of the digits matter?
If it's supposed to be even, yes.
Yeah, or just in general, when I look at a number, the order of the digits matter. If I took those digits 7, 6, 5, that's a totally different number than if I changed the order 5, 6, 7.
Right.
So order matters. So I'm not thinking combinations, I'm thinking permutations. And so my entire sample space, how many numbers do I have to pick from? There's 1, 2, 3, 4, 5 digits. And if I'm making a 3-digit number, I'm picking 3. I'm going to erase this stuff on the side. And so that becomes, and this is one case where I actually don't like using that permutation button on my calculator, but I like working it out. That says that I've got 3 blanks to fill in, and I'm going to start with the number 5 or 3. Or before we defined permutations, didn't we look at it as 5 choices for the first digit, 4 choices for the second, 3 for the third. Now, if the number has to be even, if it has to be even, I'm going to focus on this last digit, right? The last digit has to be an even one.
Yes.
And so I'm going to go look at this. And if the last digit has to be even, it means that it has to either be the 4 or the 6.
Yes.
2 choices for that digit. If you want to do it the fancy pants permutation way, for the even part, there are 2 even and I have to pick 1. Second part, if the number has to be greater than 700 would be determined by this first digit.
Yes.
And if it's going to be formed from these digits to be greater than 700, doesn't the first digit have to be the 7?
Yes.
And so there's 1 choice for that. If you want to do it the fancy pants permutation way, there's 1, 7, and we got to pick it. So now we filled in the first slot and we filled in the second slot. So didn't we use up 2 numbers, leaving me 3 to pick from? Does
Yes.
that make sense?
Yes.
And so now I leave it factored because I don't know if you guys noticed, it's easier for me to do the arithmetic in my head than find my calculator. I've reached that point in life where I set something down and it's lost for a while. So leaving it factored allows me to cancel this. And then if you multiply across, that would give you 2 over 20 or 1 out of 10. How fun is that?
Wait. Oh, so okay. So I would have to cancel out the canceling out confuses me because when I look at it,
Okay, then if the canceling out confuses you, I'm interrupting, I'm sorry.
no, it's okay.
If the canceling out confuses you,
Because when I look at that, I do like 1 times 3 times 2, and then that's my top number, and then 5 times 4 times 3.
you can do that. You see, I just got rid of the canceling out. 1 times 2 times 3 is 6. 5 times 4 times 3 is 60. And that still reduces to 1/10. That's perfectly fine.
Okay.
Okay. I guess maybe it's because I'm short. I'm scared of big things. So I'm scared of big numbers. So I cancel it out to make the number smaller. But if you're comfortable with bigger numbers, by all means, go for it. All right. And I think we discussed how you can reduce a fraction with your calculator if you're not comfortable doing that. So
Yes.
yeah. Is this one better?
Yeah.
I think the fact that it was a permutation and we were picking 3 from 5, I think the denominator is pretty straightforward. But then again, I always approach these. I find it easier to approach these by filling in the slots. If it's got to be bigger than 700, I've got 1 choice for this digit. It's got to be even. I've got 2 choices for this digit. And then after I used up one of the even numbers in the 7, I've got 3 choices left for the middle digit. Okay.
Okay.
All right. How about anybody else? Any other ones from this one? Anybody want to look at any others from this assignment?
I think it's number 8.
Find
Yeah.
the probability of getting 1 queen and 3 kings. All right. Did I make you folks suffer through my singing Sesame Street songs? Cards, as a rule, begin with C. Cards, as a rule, are combinations. Usually with cards, the order in which you get them does not matter. So I'm picking 4 out of 52. So my sample space is that 52 combination 4. And so there, damn it, now I have to find the calculator. I got it. Turning it on, clearing it, 52 combination 4 gives me 270725. Now, in the numerator, what do I want? 1 queen. How many queens are there in a deck?
4.
Anybody? 4. And how many of them do I want?
1.
The order does not matter. So for the queen, does it make sense that that's 4 combination 1? And that one I can do in my head. 4 combination 1 is the number 4. And now we want 3 kings. In the deck, how many kings are there?
4,
And how many of them do I want?
3,
3. An order does not matter. So that's 4 combination 3 for the kings. In between, we have that magic word and that the counting principle told us meant to multiply. 4 combination 3 turns out to also be 4. And so this probability is 16 over 270,725. And this one, I'm looking at this, and I was hoping that they asked for this one as a fraction, because that's not reducible. But sadly, they don't. And so they want us to turn it into a decimal. So I'm going to take 16 and divide it by that last answer. And so as a decimal, that gives me 0.12340599101. They want me to round it to 6 decimal places. 1, 2, 3, 4, 5, 6. Looking at the next door neighbor, it's less than 5. So my final answer is 0.00059.
Professor Girola, when I divided the 16 by the 27725, I didn't get that as an answer. I got a 5.91, and then it goes.
You got 5.91, and then it goes blah, 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 blah. And then at the very end, the furthest part to the right of your screen, is there something that's either E5 or something 10 times 10 to the 5th?
Yeah.
What happened was first of all, before we go any further, does it make sense looking at this answer that you shouldn't be getting whole numbers? You should be getting a pretty small decimal. The numerator's tiny, the denominator's huge. When it's written, are you the E5 or the times 10 to the 5th?
The E5.
Okay, that E5 tells you that you're in scientific notation, and it tells you got to move that decimal point 1, 2, 3, 4, 5 places over and fill in with zeros. Once you do that, it takes you to the same place.
Okay, thank you.
Okay, it's just that your calculator threw it into scientific notation for you. So, God, I've scribbled on this screen. Anybody else? This one a little bit better. Are we feeling a little bit more confident, or do you guys want to go over one more together?
Could we go over another one together? I'm
I
sorry.
which
I'm
one
sorry.
it is.
This one was
Don't apologize. I just put that out there. But this will be the last one. If you need more help after that, email me. We'll talk.
okay.
Okay. Which one?
Oh, I can pick. Hold on.
Does somebody else in the class have one? in
Yeah, does someone else
particular
want to
they
pick?
want?
No.
Okay.
Okay, can we did we go over, did we do 6?
I don't think so. Okay. 3 cards from a well-shuffled deck of 52. Okay, find the total number of possible 3-card poker hands. We said cards begin with C. I think a Cookie Monster. I'm going to try to use a combination, unless there's something in the phrasing that says order matters. So there's 52 cards in the deck, and I'm choosing 3. So when you work that out, I get 22,100 hands. So far, so good.
Yes.
Now, a red flush is a 3-card hand consisting of all red cards. So I want to pick 3 cards, but I want them to be red. How many cards in my deck are red?
13.
13 hearts. And aren't there also 13 diamonds?
Okay. I'm not too familiar with a card deck.
26. I'm going to stop for a minute. I'm going to pause and turn my finger back into a mouse. And in the mouse, I want to go to content. And in content, it's going to take its damn time. In handouts, I think I put for you. And if we were on campus, I would have printed this out and given it to everybody in the class. And if it was a handwritten in-class test, I would pass this out to everybody in class. But if you're struggling with, if you're not familiar with a deck of cards, you could go to the store and buy a deck of cards and start playing, I guess. But, and I'm being silly when I say that. There's a picture of a deck of cards here.
Oh, okay.
Okay, and so, and if you make it bigger, you can see the king, queens, jacks are base cards. The aces, the numbered cards are the 2 through 10. And the hearts and diamonds are red, and the clubs and spades are black. I did put that in there for you. I apologize. I thought I had said that before, but there's a good chance that I didn't. So that's in there for you. So 26 combination 3. I'm lazy sometimes and hate digging into that combination permutation probability menu. Since my last thing was 52 combination 3, I just arrow up and type 26 over the 52. When I do that, I get 2,600.
Yes, that's what I got.
So that's the number of ways my event can occur. That's my sample space. The probability is the ratio of those. Of those. And so I'm going to just turn those into a fraction. And let me see, I can, I think they asked that to be reduced. I think the only thing that goes into 26 is 13 and 2. Is 221 divisible by 13? Yes?
Is it 2 17ths?
Yes. Better?
Will that take it? Because there's been some times where I thought I had it reduced down to like the smallest it could go, and then I put it in and it's like, oh no, it can go smaller, it goes to this, and then gives me like a whole new question because I tried too many times, and that's super frustrating.
Do you use your calculator to try to reduce
Yes.
it? Yeah, okay. I just, you just have to kind of keep on working at it until they're relatively prime. So, on a test, if you had the right fraction and you didn't reduce it because we're doing tests on my labs, they won't give you credit. But if I'll go through and look at the problem, and if you have the right fraction and it's just not reduced, you'll get 9/10 of value. All right? Because
Okay.
again, we're worried. I'm not teaching you fractions, I'm teaching you probability. So that's what I'm most worried
That's
about.
nice. Yeah, the reducing part makes me like anxious.
Okay. How about everybody else? Is that one all right? Can I clear it?
Yep. Good.
Okay. All right. Then let's pick up from where we left off. If I remember correctly, the last thing that we discussed was the probability of an event not occurring. And I think we had said that the probability of an event, it would help if I wrote what I was thinking, I'm sorry. The probability of an event not occurring is 1 minus the probability of the event occurring. And I got the impression that everybody was pretty comfortable with that. From not, the next thing in this next section is probability involving the word or. Before we discuss about probability involving the word or, I apologize, I didn't ask. Do you guys hear me okay? Am I breaking? Or
It's
does
kind
it?
of muffled, but I can still hear
Yeah,
you.
it's kind of muffled, but I can hear you.
All right, I'll find the headphones. Oh no, the cables. Oh. There's only one USB port. That's the only concern that I have with this machine. And so I have to take out my thumb drive in order to use the headset. Does that sound better, guys?
Yeah.
Okay.
Thank you.
So before we look at or, if I'm ever muffled, please tell me because I have this thing, I can use it. The idea of what it means for events to be mutually exclusive. And we're going to say mutually exclusive events are events that cannot occur at the same time. They have no outcomes in common. We want to sound fancy rather than saying they have no outcomes in common. We can say that they're disjoint subsets of the sample space. And so let's look at an example. For an example, I want to think of rolling a die once. If I roll my die once, what's the probability of rolling the number 4?
One out of 6.
Beautiful, thank you. What's the probability of rolling the number 5?
1 out of 6.
1 out of 6. And the 4 and the 5, they have nothing in common, right? And so they would be considered mutually exclusive. And if I ask, what's the probability of rolling a 4 or a 5? Wouldn't that be 1 out of 6 for the 4, 1 out of 6 for the 5, and can't I add them to get 2 out of 6, or 1/3? And it's always going to be the case that if A and B are mutually exclusive, the probability of A or B will equal the probability of A plus the probability of B. And so let's look at another example. Let's say I have a deck of cards. I want to pick one. What's the probability that I get a king or a queen? Well, are they mutually exclusive? Are any of the kings also queens? Are any of the queens also kings?
No.
There's no overlap, so they're mutually exclusive. So that'll be the probability of a king plus the probability of a queen. And let's see, I think 4 of the 52 are kings, 4 of the 52 are queens. So that gives me 8 out of 52. And I believe they're both divisible by 4. So that gives me 2/13. Next example is going to be a little bit different. What's the probability from that deck of cards, if I pick one, of getting a jack or I'm going to try to draw here a spade? Are those mutually exclusive?
Not always, no.
Not always. Isn't there one jack that's a spade? Isn't there one spade that's a jack? So
Yeah.
no, they share the jack of spades. And so does that make sense that I can find the probability of getting a jack? That would be 4 out of my 52 cards. I can find the probability of getting a spade. That would be 13 out of 52 cards. But does it make sense that I have to subtract the overlap? Nothing counts twice. I have to subtract the probability that I get the jack of spades, the overlap. I have to subtract that one card that was being counted twice. And so that gives me 16 out of 52, which dividing by 4 would give me 4/13. And what happens is if A and B are not mutually exclusive, we're going to say that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of both at the same time. And some of that idea might look vaguely familiar. We had said that when we look at probability, we're looking at the number of ways an event can occur, an event being a subset of the sample space. So we can think back to when we were working with sets, and the sample space is our universal set. And we can, when we're trying to count the number of things, remember we said that the word or was like the union. So the number of things in A or B is the number of things in A union B. And didn't we say that that's the number of things in A plus the number of things in B minus the number of things that they have in common in their intersection? And does that formula for cardinality look vaguely familiar?
Mhm.
And so we will be using that idea again when the course was put together. it was written to help people get ready for taking our statistics class. And so the people in statistics really wanted you to take the statistics and the probability. And they added sets for this reason, to show you how, why things occur the way they do. And so let's look at one more example. Let's say I'm going to roll a die once, and I want the probability that I get an even or a number that's less than 4. So it's an or. We've got to take the probability of an even. We have to add to it the probability that it's less than 4. And then we have to say to ourselves, is there anything that we're counting twice? Are there any evens less than 4? My die has 6 outcomes. Of those 6, how many are even? 2, 4, 6, 3. Of those 6, how many are less than 4? See, that's 1, 2, and 3, so that's 3. But now, are any of the numbers less than 4 also even?
Yeah.
Mhm.
2.
And the number 2?
Yeah.
So we have to subtract for that 1. And so that gives me 5 out of 6. And does this formula make sense to everybody
For now.
for now? There'll be some practice with it in the homework.
Yeah.
If that's all right, I'm going to add a page. And then the next place that we're going to go to is the idea of odds. Has anybody ever heard of odds? Usually when I think of that word odds, I think of all things, this is the Super Bowl, and they always talk about the odds makers trying to decide who's going to win, and they talk about what are the odds. And a lot of people use that word odds interchangeably with probability. They are related, but they're not the same. If I look at an event, if the odds in favor of an event occurring is a ratio, it is the ratio of the probability of the event occurring to the probability of the event not occurring. And so that's too much writing for me. If my event is E, we'll say the odds in favor of E is the probability of E to the probability of not E. And again, we said the probability of not E is always equal to 1 minus the probability of E. That's the definition of odds in favor. Does everybody have the words down so that we can start looking at a couple of examples? You ready?
Yes.
So let's say I have my deck of cards. I'm going to pick one. I want to know the odds in favor of getting or let's say getting an ace. In order to find the odds, the first thing we have to do is we have to find the probability of the event. What's the probability of an ace? Of my 52 cards, how many are aces?
4.
4. And I'm going to reduce this to 1/13 because with odds, I do like to reduce kind of early on. It's easier for me to be working with those smaller numbers. Now we want the probability of not getting an ace. And so that's 1 minus the probability of the ace. And so that's going to leave me with 12/13. And if you figure it out this way, these two fractions usually have the same denominator. So now the odds in favor of an ace would be the ratio of the probability of the ace to the probability of not getting the ace. So it's the ratio of 1/13 to 12/13. But that looks ugly because of the fractions in there. So we're going to do a little bit of arithmetic to gently massage that. When I have that ratio 1/13 to 12/13, does everybody remember a ratio is a fraction? So I can think of that one in front of the colon 1/13 over the one behind it, 12/13. And oh my God, doesn't that look even worse? Fractions inside of fractions.
Yeah.
But remember that a fraction can also be thought of as division. So that's 1/13 divided by 12/13. And in order to divide fractions, does the phrase keep the first one the same, change the division to multiplication, and flip the second one? Keep, change, flip, or multiply by the reciprocal. And then here, I'm sorry, I am going to cancel. And that leaves me with 1/12. So I can reach that, rewrite that, pardon me, as the ratio 1 to 12. So I've got 1/13 to 12/13. And I'm going to rewrite that as the ratio of 1 to 12. Does anybody think that that arithmetic that we just did was a bit of an effort, a bit work?
Yeah.
I'm talking to a room full of intelligent college students. Can anybody see how I could have gotten that 1 to 12 from the fractions 1/13 to 12/13?
Oh, you just take the denominators out.
Yeah, and as long as the denominators are the same, it will be the ratio of the numerators. So if the denominators are the same, it's the ratio of the numerators. Oh, what's that pop-up? I hate those little pop-ups. Sorry about that, folks. Did you see the pop-up that came up on my surface or no?
Wasn't looking, but
Okay, thank you. That made my day. And do you notice that the odds are different than the probability? The probability was 1/13. The odds are 1 in 12. So odds are different than probability.
I have a question.
Yeah,
Are the two dots does that just mean like ratio?
that's ratio.
Okay.
So over here, when I write 1:12, that means the same as 1/12, but I read it as 1 to 12.
Okay.
Okay. We also talk about the odds against an event. The odds against E is the ratio of the probability of not E to the probability of E. And so what were we looking at? Odds if I wanted the odds against, and I meant to say we were looking at aces, right? An ace. That would be the probability of no ace to the probability of an ace, which would be our 12/13 to 1/13, which would reduce to 12/1. And this is where I see a big difference between probability and odds. Because if I look at that 12/1, as a fraction, that's the fraction 12/1. And do you notice that odds can be greater than 1?
Yeah, that's true.
Probability is never greater than 1. Odds can be greater than 1. Something can happen more than half the time. Its odds will be greater than 1. If something's going to happen less than half the time, its odds will be less than 1. If something's happening half the time, it's like a 50-50 split. It's the odds will be 1-1 or equal to 1. Now, there's also a point, there are problems in the homework. There will be problems on the test. And something that you'll need to be able to do for the project for this chapter is look at the relationship between odds and probability. And we looked at how to turn probability into odds. Now we want to look at how to go from odds to probability. And in order to do that, I want to look at another example. Let's say, again, I got my deck of cards. Let's say I want the odds in favor of getting a heart. The probability of a heart, there's 13 hearts out of my 52 cards, so that's 1/4. The probability of no heart is 1 minus 1/4, which is 3/4. So the odds that favor a heart would be the ratio 1/4 to 3/4, which would be 1-3. Now I want to look at how this answer compares to my probability. And do you notice that the first number is the same as the numerator? And do you notice that the denominator turns out to be the sum of the two numbers? And so we'll say that if the odds in favor of an event are A to B, the probability of the event is A over A plus B. And so one more example of that. Let's say the odds of winning a game are, I don't know, does somebody want to give me a number?
2 out of 7. I don't know.
Nobody has a favorite number? All right, we'll make it up. 2 to 7. What's the probability of winning? That's my ratio A to B. And it said the probability is A over A plus B. So wouldn't that be 2 over 2 plus 7? Or 2 nines? One more example? Is that all right with everybody?
I think so.
Yeah.
One example, let's say the odds of losing are 15 to 2. What's the probability of winning? Well, if the odds of losing are 15 to 2, that's the odds against winning. What are the odds in favor of winning? Wouldn't that be 2 to 15? The odds in favor and the odds against are reciprocals.
So it's basically just the opposite.
If we go back to where we defined them, I'm going to flip pages for a minute. We said odds in favor are the probability of the event to the probability of the event, not the event, and the odds against to the probability of not the event to the probability of the event. So we are going to just flip them. So if the odds of losing are 15 to 2, not losing is winning. The odds of winning are 2 to 15. And so the probability of winning would be the first number over the sum of the two. So it would be 2 over 7. So far, so good?
Yep.
Then this is doing it in a weird order. I'm going to have to delete pages. I apologize. Next, let's look at the idea of independent events. And we're going to say that two events are independent if the occurrence of one does not influence the occurrence of the other. So two events are independent if the occurrence of one does not influence the occurrence of the other. What happens on one has absolutely no effect on what happens in the other. And so let's say, for example, I toss 2 coins. The first coin can either be a head or a tail. The second coin can either be a head or a tail. What the first coin is, does it at all affect what the second coin is?
No.
No, so they're independent. What if instead I roll 2 dice? Does the number that shows up on the first die have any influence at all on the number that shows up on the second die? No, I don't think so. And so those would be examples of independent events. And we're going to say that if A and B are independent events, probability of A and B is equal to the probability of A times the probability of B. And actually just goes back to our fundamental counting principle, where we said that the number of ways two independent events can occur, I'm going to multiply. And so let's look at that toss two coins. What's the probability that both heads? Well, if they're both heads, isn't that asking what's the probability of getting a head and a head? So we have the probability of the first head times the probability of the second head. So on my coin, what's the probability of the first toss being a head?
1 of 2. 1 over 2.
Second one would be
1 over 2.
2. And so both heads would be 1 over 4. Next example totally oversimplifies genetics. But let's say we have a family with 4 kids. What's the probability? They're all girls. Well, if I look at my family, the gender of my older siblings had absolutely nothing to do with my gender, and my gender had nothing to do with that of my younger sibling. So, what one kid is has absolutely, whether they're a boy or girl, has absolutely no influence on whether the second one is. Are we in agreement here?
Mm.
And we're going to oversimplify genetics and say the probability of a girl is 1/2. And so if I've got 4 kids, 1, 2, 3, 4, the probability that the first one's a girl is 1/2. The second one is 1/2. The third one is 1/2. The fourth one is 1/2. And while I don't see the word "and" in there, does it make sense if I want the probability of 4 girls? It's the probability of a girl and another girl and another girl and another girl. And so multiplying, that gives me 1 over, let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16. Make sense?
Yep.
That next example, I want to look at a deck of cards. I'm going to pick one. I'm going to replace it. I'm going to shuffle it, the deck. I'm going to pick a second. I'm going to pick again. And I want to know what's the probability that they're both, let's say, hearts. Now, I pick a card. The probability of the first one being a heart would be 4 out of, oh Lord, no it wouldn't. Let's try that again. What would it be, 13 out of 52? Now, if I'm taking that heart and putting it back and shuffling again, these are independent, aren't they? And the probability that the second one of the heart being a heart would still be 13 hearts out of 52 cards. And this one, when I multiply, I think it's going to be easier if I reduce first. It's 1/4 times 1/4, which gives me 1/16. And I want to compare that to the next, where I have a deck of cards. and I pick 2 without replacing. What's the probability they're both hearts? This time, if I'm not replacing, the first one, it's 13 out of 52. But for the second one, would it still be 13 out of 52?
No.
No, it would be 12 hearts left out of the 51 cards left. And these are not independent. The first heart changed the probability of the second one. And so when I go through and multiply these out and then reduce, that gives me 117. And that takes me to a new idea, which is conditional probability. Can I turn the page?
Yeah.
And so we're going to introduce a new notation, the probability of, there's going to be, then a bar, then A. And we're going to read that as the probability of B given A occurred. And we're going to say that if A and B are not mutually exclusive, the probability of A and B is equal to the probability of A times the probability of B given A already occurred. And it's like when we don't replace that card, the probability of the second one changes. And so I'm looking, something's missing here. Okay. Oh, where did that come from? I'd like to look at a whole bunch of examples of these. And for examples, I'd like to pull problems from this worksheet that I had put in Blackboard for you. It's the conditional probability examples. Before we do that, oh yeah, let me just go to that page. Let's look at first, here I've got questions 15 through 20 up at the top. You draw one card from a deck of 52 cards. Then the card is replaced in the deck is shuffled, and you draw again. Find the probability of, let's look at number 16, getting a jack the first time and a club the second time. Is everybody all right here because they're being replaced and shuffled? We can say that they're mutually, I apologize, not mutually exclusive. We can say that they're independent. So for the probability of first a jack and then a club, that would be the probability of a jack times the probability of a club. And for jacks, there are 4 out of 52. And for clubs, there are 13 out of 52. And so when I multiply and reduce, that will give me 1 out of 52. What's the probability of getting a black card each time? Well, that would be the probability of a black times the probability of a black. When we looked at that deck of cards, we saw that half of the deck, or 26 out of the 52, are black. Because we're replacing and shuffling, there's still 26 cards that are black out of the 52 cards that are left. Or I can think of that as 1/2 times 1/2, which would give me 1/4.
Wait, wouldn't this one not be independent? Because if it's a black card each time.
But we're still replacing and shuffling,
Oh, okay. Sorry.
okay? I'm gonna skip down to question number 26. I have no idea what that little doohickey thing is in the middle of the page, but okay, 26 says the probability that a region prone to flooding will flood in any single year is 1/10. What's the probability of a flood 2 years in a row? So I guess I'm wondering, is that independent? Did the amount of rain that we had last year have anything at all to do with the amount of rain that we had this year?
No.
No. So we're going to say that the weather is independent from year to year. So the probability of rain in the first year is 1/10. The probability of rain in the second year is 1/10. I'm sorry, not rain, floods. Floods are a little bit more than rain. So multiplying across, it gives me 1 in 100. What do you think we're going to do to find the probability of rain 3 years in a row?
Would we just do that 3 times?
Beautiful. 1/10 times 1/10 times 1/10 would give me 1/1000. Now this one asks for the probability of no flood. Well, if the probability of a flood is 1/10, what's the probability of no flood?
10/1?
We're talking probability, so I see where you're coming from. That would be like the relationship if we were talking odds, but with probability, we don't just flip it. Do you remember with no, we subtract from 1?
Yes, yes.
So that would be 9/10. So no flooding for 10 years, wouldn't that be 9/10 times 9/10 times 9/10? And I'm getting sick and tired of writing it. Wouldn't I be taking 9/10 and multiplying it by itself 10 times? And this one I'm going to do as a decimal. So let's take 0.9 to the 10th gives me 0.349 if I round it to 3 decimal places. And so the next one's interesting. It asks, what's the probability of at least once in the next 10 years? That at least once, doesn't that mean 1 or more?
Yes.
Well, wouldn't I have to figure the probability of 1, the probability of 2, the probability of 3, and so on, and add them all? But now, wait a minute. if I think about that, probably 1 year, 2 year, 3 year, 4 year, and so on, doesn't that exclude the probability of no floods? And so we're going to say, and I'm going to go back here, the probability of something occurring at least once. That's the complement of it never occurring. So it will be 1 minus the probability of it never occurring. And so playing hopscotch, over here, the probability of at least once would equal 1 minus the probability of none. And didn't we just find the probability of none in 10 years? So that would be 1 minus the 0.349, which gives me 0.651. And damn it, I wanted to get further than this, but I'm looking at the clock and we have 1 minute left. So we'll stop here. We'll pick up from here next time. I might tweak the, no, we went through not or odd. So we're good with the due date on homework 11. Let me real quick go back and look at homework 12 will be due on the 22nd instead. So I'll go back and I'll make sure I change that. Oh, why did we run out of time? Why does it always happen? Did it go fast or was it just me?
It did go fast for me.
Go fast, yeah. Well, hopefully time flies when you're having fun. Hopefully it means it's going well. I'm going to stop recording.